Student, I am continuing. Hello, student. I am continuing this long wavelength limit, the second case of this monatomic lattice. For longer wavelengths, k tends to 0 because k is equal to 2 pi by lambda. As lambda increases, k decreases. So that is why k tends to 0. And this sign of half ka, the sign of half ka becomes half ka because this half ka is a very small quantity. When theta is small, sin theta can be written as a theta. So that concept is used here. And the equation 6 becomes like this. It means the dispersion relation becomes like this. So we have written like this. So here sign of half ka becomes simply half ka, and simplify this one. You'll get this as a ka into root of beta upon m. So this shows that omega is proportional to k. Omega is proportional to k. That means the frequency omega is a linear function of a wave vector k, and therefore the velocity of sound waves in the long wavelength limit is independent of frequency. So in the velocity expression there will be no k. That means uh, velocity of the wave is independent of the frequency in this case. Then the group velocity is given by Vg is equal to d omega by dk. You differentiate equation 7, and this becomes a into root of beta upon m, and this is keep this as omega naught, v naught, and the phase velocity is given by Vp is equal to omega by k, and this is equal to a into root of beta upon m, and this is also v naught. So thus in this case the phase velocity and group velocity are equal, and each is equal to a constant, that is v naught. We therefore conclude that for very long wavelengths, the dispersion effects are negligible, and the medium acts like a continuum and homogeneous medium. So for longer wavelengths, what happens? The dispersion effects are negligible because the velocity do not depends upon the wave vector or the frequency, and thus the medium behaves as a continuous and a homogeneous medium. Now we'll see the case of shorter wavelength limit. So if at shorter wavelengths k is a larger quantum value and omega is no more a linear function of k, and that sign of half ka, that half ka quantity is not small now, it is a larger quantity. So therefore then the phase velocity and group velocity are different, and they are given by Vp is phase velocity is equal to omega over k. This is equal to root of beta upon m into sine of ka by 2 into 1 over k. That means we have divided the equation 6 dispersion relation by k, and simplify this equation like this. Take 4 outside the root and becomes root of beta upon m sine of k by 2 into 1 by k. And here you will multiply and divide by a. So lastly it takes this form 2 upon ka into v naught into sine of k by 2. Here v naught is equal to what is that? A into root of beta upon m, and that is v naught, as in the earlier case. As in the earlier case, v naught is equal to a into root of beta upon m. That is a constant. So it is the expression. Equation 10 is the expression for phase velocity. Then a group velocity by definition is d omega by dk is equal to 1 over t, and differentiate equation 6 dispersion relation you will get like this, and go on simplifying like this. To get cancelled, and again we are getting vg equals v naught into cos of 1 over 2 ka, where v naught is again a into root of beta upon m. So it is clear from equation 10 and 11 that the velocities are functions of frequency. Hmm? So in the longer wavelength, the velocities are not dependent on the frequency, but now in the shorter wavelength, in during for the shorter wavelengths, the group velocity and phase velocity becomes the functions of frequency. So the dispersion effects are very important at the shorter wavelengths. As you know, k is equal to 2 pi by lambda. This is equal to 2 pi. Lambda is written as a nu over v using the standard relation. Nu is a frequency, v is a velocity, and this nu is equal to c upon lambda. As you know, that can be written as a v upon lambda for a given medium, where v is the velocity of the wave. Hence, the medium becomes a dispersive medium. The medium becomes a dispersive medium for shorter wavelengths. Next, we see the Bragg reflection. Bragg reflection at the maximum frequency limit k is equal to 5 by a means the Brilliant zone condition, the Brilliant zone boundary. The first Brilliant zone is bounded by k is equal to plus 5 by a and minus 5 by a. At these two values of k, the frequency is a maximum. That is what is called as the maximum frequency limit. And sine of half ka is equal to 1. Put k is equal to half a here. So everything get k, what is that? A and 2 get cancelled. Lastly, we are getting sine phi. Sine phi uh, is sine of 5 by 2 left there. So sine of 5 by 2 is 1. But k is equal to 2 pi by lambda, and thus what is that? But k is for this case, k is also equal to 5 by a, and equate that. So 2 5 by lambda, this 2 5 by lambda is equal to 5 by a. So from that, lambda becomes equal to 2a. So using above conditions in equations 10 and 11, we have expressions for mm, sorry, we have we are here. Uh, so we are here. So using above conditions in equations 10 and 11, we have Vp group velocity becomes 2 V naught upon K, because sine of K by 2 is there. Put the value of lambda is equal to 2a and go on simplifying, that becomes equal to 1. So therefore phase velocity becomes equal to 2 V naught by Ka. And similarly, here, when Vg for group velocity, we have to differentiate the dispersion relation. It is d omega by dk. When you are differentiating the sine Ka by 2, it becomes cos Ka by 2, and you are putting the value of that lambda, and you are simplifying, it becomes cos phi by 2. Cos phi by 2 is 90 degree. So cos of 90 becomes equal to 0. So therefore, the group velocity is 0. So since the group velocity is 0, there is no transfer of energy, and hence the wave is a standing wave. As you know, the standing waves are the waves which do not carry the energy due to some reflections at the ends of the vibrating medium. The standing waves are formed. So at this value of k, the Bragg condition is satisfied, and hence the wave is reflected to and fro. Thereby, standing wave is set up. Next, we'll see what range of values are important in this whole study of monatomic lattice. From equations 3 and 5, we take the ratio of displacements of two successive planes like this. So this xn is given by this value, a into e raised to I into omega t minus kna. Xn plus 1 is given by this quantity, and divide these two, a get cancelled, all other quantities get cancelled, it becomes e raised to ika. So in this way, you can take the successive division of any displacement. Always you will get e raised to I k a. So this tells that a range of values k lying between k is equal to 5 by a and minus 5 by a covers all independent values of e raised to I k a. Hence, only this range of k are important. The positive and negative values of k are considered because the lattice wave can propagate either forward or backward direction. So, the zone covered by this range of independent values of k is referred as a first Boolean zone. That means k is k when the for the k is equal to plus or minus 5 by a range, whatever is there, and that is called as the first Boolean zone. Similarly, there will be second Boolean, third Boolean zones like that. Boolean zones are there. So for each region outside the first region, that is first Boolean zone, the physical character of solutions is same as for the first zone, except for a translation along k axis by a distance equal to an integral multiple of n5 by a, where n is equal to 2, 3, 4 is corresponding to second, third, and zone. That means whatever properties possessed by this first Boolean zone is there, all those properties are exhibited by the second Boolean zone and third Boolean zone like that. So therefore, the second Boolean zone, third Boolean zone, all those are they are the replica of the first Boolean zone, and hence if you study the first Boolean zone range, that is more than enough. So that is why only the values of k lying between the first Boolean zone are very important. And next we will see what are the normal modes of vibrations of this one dimensional monatomic lattice of finite length. So here I have taken a one dimensional chain of monatomic lattice. You see it is having a length of capital L, and both the ends of these chains bound to a rigid support. Therefore, the vibrations are zero at both the ends. The atom which is present at the extreme left end is n is equal to 0 and n is equal to 1, 2, 3, 3, dash 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 like that, n minus 1, and n atoms are there. In this chain, there are capital N number of atoms. So consider a one dimensional lattice of finite length. Let there be n plus 1 atoms because n is equal to 0 is there, uh, of length L at a separation of A. A is a lattice parameter here because it is the distance between two successive atoms. So therefore, A is a lattice parameter, and every atom is separated by a distance of A, and numbered n is equal to 0 to n is equal to n. When a wave is moving in the lattice, it is reflected from the fixed end, and a standing wave is generated because this lattice is this chain is bound at both the ends. Therefore, vibrations are not there at the both the ends. Therefore, the waves gets reflected back. So the standing wave formation is there. This standing wave is represented by this equation: xn is equal to xn x naught into sine of k and a into sine omega t. The boundary conditions for this case are xn is equal to x naught is equal to 0. The x naught is equal to 0 means it is the left hand, and xn is equal to 0 means it is the right hand. So at at both the ends, the atoms are not vibrating because they are bound to the rigid rigid support. So therefore, the displacements are zero. This is the boundary condition which satisfies the equation one. It is if that is the case, then you take a sign on this condition two. So sine of k and a is equal to sine of k and a is equal to 0. Or from this right part, sine of k capital N a is equal to 0. That can be written as kNa. This kNa equals sine inverse of 0. Sine inverse of 0 means it is 0, 5, 2, 5, 3, 5, dash, dash, dash. Or k is equal to 0, 5 by Na, 2, 5 by Na, 3, 5 by Na, dash, dash, dash. So in this way. So where Na is equal to L, the length of the this lattice monatomic lattice chain, where capital N represents actually the number of atoms and A is the separation between two atoms. So the length of the chain. Thus K is equal to, I will substitute Na as a L in this equation, in the above equation. So this becomes K is equal to 0, 5 by L, 2 5 by L, 3 5 by L, dash dash dash. And here K is equal to 0 corresponds to the state where all atoms are at rest. K is equal to 0 state means for the first atom, so it is not vibrating, so that is the atom is at rest, and also the last atom is also not vibrating. Thus for that K is equal to capital N phi upon L. So this because it can be shown like this, xn is equal to x naught into sine of n phi by L into Na into sine omega t. So you just go on simplifying, the sine of capital N phi becomes 0. So therefore whole thing becomes 0. So that means xn is equal to 0. This can be shown using trigonometric relations. So this implies that displacement is 0. That means all atoms are at rest only at x is equal to 0 and xn is equal to 0. Hence these two values of k are omitted. The first k value and the last k values are omitted because it corresponds to the atoms which are bound to a rigid support. So these are the, and we thus conclude that first one I am omitting, k is equal to 0 case. So the remaining are k is equal to 5 by L, 2 5 by L, 3 5 dash 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 n minus 1 5 by L, and here it was n 5 by L, that is omitted for the last atom. And therefore there are n minus 1 allowed independent values of k. This number represents the number of atoms allowed to move. Hence there are n number of normal modes of vibrations. So the normal modes of vibrations depends upon the number of degrees of freedom. So how many atoms are free, that is very important. So here n minus 1 number of atoms are free to move. So therefore, there are n minus 1 number of normal modes of vibrations. So this concept is applied. So it's all about monatomic lattice, and this is very very important for examination point of view, and you should take care of that. Immediately we have to prepare. Thanks for listening.